So this is going to seem very familiar because it is. Limits at infinity discuss end behavior. So I'm not talking about where your limit is infinity, right? Limit is infinity means that it's shooting off like up towards infinity or down to negative infinity. This is a limit that happens when x is approaching infinity, okay? And so for the other ones that we've looked at where your limit itself is positive or negative infinity, then your x is usually approaching a specific number. But here we're going to look at what happens when x itself is approaching positive or negative infinity. All right. And so you see the way they show this, right? This is a horizontal asymptote. And then you can see that x is shooting off towards infinity because it's getting ever so close to that asymptote, but it's not touching it. And then you can see what it looks like when you actually do a chart. As you have this 3 value here on either side of it, and you can see that x is going towards negative infinity on the left and towards positive infinity on the right. And then we see the actual definition here. Let L be a real number. The statement at the limit as x approaches infinity of f of x equals L means that for every epsilon greater than delta, there is an m greater than 0 such that, and that is your limit definition, f of x minus L is less than epsilon, wherever x is greater than m, and so on for the negative infinity as well. So basically what we're doing is we're trying to figure out the y value as x goes towards positive or negative infinity. And what happens is you end up finding horizontal asymptotes, all right? And so if you look at the next page, you see the definition of a horizontal asymptote. The line y equals L is a horizontal asymptote if, as x approaches negative infinity of f of x equals L, or as x approaches positive infinity, f of x equals L. So basically your horizontal asymptote represents the limit as x approaches positive or negative infinity. And because of that, you have this beautiful shortcut that happens with infinite limits, right? Because if you remember, you have a shortcut for horizontal asymptotes. If it is greater degree on the bottom, your horizontal asymptote is 0, which means if it's greater degree on the bottom, then x is approaching 0. Y is approaching 0 as x goes to infinity. If the degrees are the same on top and bottom, you use your coefficients. And if it's the top, we've always said there is no horizontal asymptote, which means in this case, x is going to also approach infinity. Y is also going to approach infinity as x approaches infinity. And so you use those same shortcuts when you're doing limit theory. They have some theorems here. If r is a positive rational number, and they define this as x approaches infinity for some constant over x to a power, you're going to be approaching 0. Whether you're going to positive or negative infinity, your value is still approaching 0. Well, why does that work? Well, your shortcuts. What is your degree of a constant? Your degree of a constant is 0. Here you have a degree larger on the bottom than the top, so your limit is approaching 0. That is the same shortcut we've always used. Let's think about this logically though. Your numerator is some constant, 1, 2, 3, 4, 5, just a number. Your denominator is x to a power. X is approaching a really large number here, right? X to a power. The numbers at the top staying constant, the denominator is getting infinitely larger. That fraction itself is getting small. 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000. That fraction is approaching 0, which is what the limit would be. All right. So the first thing we're going to say is if there's a constant on top and an x on bottom, and your x is approaching positive or negative infinity, it doesn't matter which one, that fraction itself's limit is going to be approaching 0 because the fraction itself is going to be getting tinier. And by tinier, I mean either from the right-hand side towards 0 or from the left-hand side, it's going to moving towards 0. Right? Either way, it doesn't matter what x is doing as far as positive or negative infinity. If you have a constant on top and an x on bottom, and that x is approaching either infinity, that fraction itself, absolute value, is getting smaller, meaning it's moving towards 0. All right? So let's look at the application here. The first one is find this limit. Well, the limit of the constant doesn't change, hence the term constant, right? So the limit of this 5 is going to be 5. Make sense? Because there is no x to evaluate there. So the limit as x approaches x approaches infinity of 5 is just going to remain a 5. The limit as x approaches this guy here, as infinity for this guy, well, my 2 is not changing. My x squared is getting infinitely larger, which means this group here is approaching 0. Constant over an x as x approaches an infinity. So my overall limit is just going to be those two together. 5 minus 0, my overall limit is just 5. Easy enough? Make sense? My constant's not changing. My denominator is getting infinitely larger. That piece is approaching 0. The 5 doesn't have an x in it to be even bothered by the x approaching infinity, so it stays in 5. 5 minus 0, my limit is 5. Let's look at the next one, which is on the next page, example 2. All right. So for this one, I completely ignore the minus 1 and the plus 1. Why is this? Well, we're talking about x approaching infinity. If I have $10 and lose $1, I will notice. If I am Bill Gates and lose $1, I may not, right? Because when we are talking about an infinite times 2 minus 1, this 1 does not bother it. Some infinite plus 1, these ones don't bother it. So when you're looking at this type of problem where you have like a binomial on top and a binomial on bottom, really the only thing that affects it is your greatest degree, okay? And so for this one, x is approaching infinity, all right? Well, you can think of it this way. This guy is going to infinity. This guy is going to 2 times infinity. These are the same degrees. My shortcut would say use your coefficients. And so if you use your coefficients here, you will recognize that this is approaching really an infinity over an infinity that's going to get rid of it. And so you really just use your coefficients. 2 over 1, my limit here is 2. Infinite limits. Because basically what you're saying is I have 2 times infinity minus 1. That minus 1 is insignificant. I have 1 times infinity plus 1. Right? These guys don't affect it. My infinities pretty much cancel out. And I'm left with 2 over 1. Right? And that's why this shortcut works. Because the infinities kind of cancel each other out. But if my degree on bottom is larger, then the larger one on bottom is going to be growing infinitely larger than as fast as the top one's growing. And so that's why it's approaching 0. But if they're the same, they're growing at the same rate. The only thing that's affecting them is the coefficients. And so you can just drop everything else and look at your coefficients, and that becomes your limit. Okay. Right? This is what we use when we do horizontal asymptotes in pre-calculus, right? This is the same setup. We look at degrees. So for this first one, my degree on bottom is larger than my top, which means my denominator is growing infinitely faster than my bottom is growing infinitely faster than my top. So here, my limit is going to be approaching 0. All right? Here, they're growing at the same rate, squared over squared. So I only have to evaluate my coefficients here. This limit is approaching 2 over 3. Now for this third one, if we were in pre-calculus, we would say it does not have a horizontal asymptote because my numerator is growing infinitely faster than my denominator, which means it's technically approaching an infinity. So when you come to limits, now I'm going to have an infinite limit. All right, technically I'm not going to have a real number limit because infinity is not a real number, right? Infinity is a concept. But in the infinite limit world, I'm actually approaching an infinity. So with this, you really just have to decide, am I approaching positive or negative infinity? Okay, so if your degree on top is larger, you will either be approaching positive or negative infinity. All right, you just have to decide which one. Now, I do this based off of my degrees as well. This guy here is easy because he's approaching positive infinity for my x value, which means I'm going to put a positive guy in here and cube it. Positive. I'm going to put a positive guy in here and square it. Positive. So positive over positive, I will not have a real limit. In the real world, you would say you do not have a real limit. But I can say this is approaching positive infinity.
Why do you put positives in the x's? Is it
Because it's approaching positive infinity, right? Had it been negative, I would have put negative in the x's, and it would have been approaching negative infinity. Okay? So when you have degree on top larger, you are going to have an infinite limit. You will not have a real number limit. I'm reiterating this because if you have a standardized test like an ACT that does limit theory, and I'm not even sure if you would have something like this on your ACT, but let's say you did, there are going to be cases where it'll say, what's the real limit here? What's the real limit? You would say does not exist, right? Because infinity is not a real number, okay? And so if it asks for a real number as your limit, you don't have one. But if it asks for the limit, the overall limit, is approaching positive infinity. So your y value is going to shoot off on this side towards positive infinity is what's going to happen, okay? Make sense? And these are the shortcuts I've been saying the whole time, but they just wrote it out for you. If the degree in the numerator is less than the degree of the denominator, you're approaching 0. If they are equal, you're using your ratios of your leading coefficients. And if the degree is greater, the limit of the rational does not exist. You do not have a real number limit if your numerator is greater. Now, again, I am going to say, for my purposes, I'll usually ask you to put positive or negative infinity there. But your real number limit does not exist. Does not exist. So let's look at some unusual ones here. Let's look at some that are a little more unusual than others. Look at your next examples here. A, B. All right, and I show you the graph down there for that particular one. All right. We have the limit as x approaches infinity for this guy and the limit as it approaches negative infinity for this guy. All right. So as we approach positive infinity and negative infinity, so positive infinity, we have x over x squared. But you'll notice on the bottom, it's the square root of x squared. Is it not? So if I were to take this guy, and I'm just going to rewrite it a little bit here. They do it a little bit longer than I'm going to do it. So, you can do it my way or their way. I don't care. All right. But really that -2 and +1 when we're talking about infinity are insignificant. Does everybody agree? And so I'm just going to look at the 3x over the square root of 2x squared. All right. I can simplify the square root of 2x squared because x squared has a root, right? And I'm talking about positive infinity, so I don't have to worry about my absolute values here. So I can actually rewrite it to be the limit as x approaches infinity of 3x over the square root of 2x. Now what do you notice about those degrees? They have the same degree, technically, all right? And so when you have the same degree here, then you just use your coefficients. And so my limit here is actually going to be 3 over the square root of 2. 3 over the square root of 2. Make sense?
Do you want us to...
So negative here does cause a little bit of an issue because we're approaching negative infinity. Now, it doesn't cause a problem in the radical because the radical is going to square. And so it will be positive in the radical. But when I do this little method here, when I rewrite it as it approaches negative infinity, I'm going to have 3x on top, and I'm going to have the square root of 2x on bottom here, right? But what happens in the bottom is I have to consider the fact that I took it out of a root, and it's the negative root. It is the negative root here, okay? And so when you start considering the fact that you have a negative root here, you actually have to kind of negate this guy. Because I took the square root of a square, and I'm talking about the negative root here, right? And so then when I look at negative infinity, by taking it out of the root, I had to go ahead and put a negative here. And so this will be negative, and then this will be negative of a negative. So this guy is actually going to be a negative 3 over square root of 2. because I took a square out of a root knowing I had to consider the negative root of it. Does that make sense? So I knew I had to consider the negative root, whereas here I didn't have to worry about the negative root because I knew I was approaching positive infinity. But when I took it out of the root here, so let's say I have the square root of 9, like x squared equals the square root of 9, right? Then I know I have just positive or negative 3 when I answer those questions. So on the approaching positive infinity, I know it was the positive root of x squared, positive x. When I was approaching negative infinity, it's the negative root of x squared, which is negative x. Does that make sense? And so when I do this little shortcut here, and I'm taking it out of a root, I have to consider the negative root. All right, and now I'm going to say what happens with negative infinity here. Well, this is going to become 3 over negative square root of 2, which is a negative answer there. So my answer for this guy is going to be negative 3 over the square root of 2. So with that last example, or the example before the last one, we had degree on bottom bigger, that's a 0. Degree is the same, leading coefficients. And degree on top, you don't have a real limit. But like I said, you do have an infinite limit. And so those are the cases where you have to just decide, okay, I know I'm going to have an infinite limit. Now I just have to figure out, is it positive or negative? It's literally all you have to do with these, okay? So let's look at these. This is easy, okay? Clearly my denominator is, I don't have one. So we're going to approach infinity. I'm going to approach infinity if I don't have a denominator, okay? Which one am I going to approach? Well, it depends on what you're plugging in. For this one, I'm plugging in a positive, and I'm taking it to a cube. It's going to remain positive. So I am approaching positive infinity. For this next one, I am plugging in a negative number of some sort, and I'm taking it to the third power, which will make it negative. So this guy is approaching negative infinity. It's literally all you have to do when you know that, hey, I don't have a denominator to either zero it out or use coefficients. Or some cases where my numerator is bigger than my denominator, right? Any of those cases, your limit will end up being an infinity, either a positive or a negative infinity. You just have to figure out which one. Look at the next group. This next group actually has denominators. All right? So when I am just handed this problem, the first thing I'm going to say is, what is my degree? My degree on top is 2 and the bottom is 1. This immediately tells me I'm going to have an infinite limit, okay? I should figure out which one it is. I will say for the most part, this guy doesn't come into play very much, because if I take 2 times a ginormous number and square it and subtract 4 times that number not squared, right? Really, this guy's going to control what happens. Does that make sense? Mm-hmm. Okay, this guy's going to really control what happens. So when you're looking at these, they actually did it where they divided it out, and I do it a little bit differently. I just decide what's happening in the numerator and what's happening in the denominator. And then I say positive over positive, positive over negative, negative over negative, right? And I just decide, is it going to be positive or negative that way? I don't do long division, which is basically what they did. I don't do that, okay? I just figure out what's happening with a positive or a negative, all right? So let's look at this first one. These are 2 identical problems. One is approaching positive, one is approaching negative, all right? So let's look at the first one. I plug in a positive and I square it. What is my numerator going to be? Positive. I plug in a positive in the denominator. That is going to be a positive over a positive. What am I going to get then? I'm going to get a positive infinity. Right? Easy enough. Look at the next one. I put in a negative and square it. What's my numerator going to be? It's going to be positive. In the denominator, I just put in a negative. What's that going to be? Negative. So I am approaching negative infinity. That is how I do it. I do not do long division.